Okay, so next I'll be doing rotational motion 2, problem 2.7. So essentially we're given this scenario where we want to determine the rotational inertia and the mass of a uniform 0.80 meter radius flywheel that we need to buy. And we want to buy this so we can go through all these restrictions. So basically what we're told is that we're dropping from 10 meters high, and by the time we reach the ground, we need to have reached a final velocity of 2 meters per second. We're also told that the mass is 80 kilograms, and the radius of the cylinder, or the radius of the flywheel, is going to be 0.80 meters. So, first to just diagram this, just to get an idea of what's going on. The circle is the flywheel, and the box attached to the rope is the mass. And just to analyze our forces and understand what's going on, we have mg pulling down, I designated that as positive, and tension of the rope pulling up on the mass, which I put as negative. So this can tell us that our sum of the forces is just going to be mg minus tr. So manipulating these equations a bit and plugging in our values for mg as 80 kg into 9.8 meters per second squared, and we know what ma is already going to be, and we can solve for ma because we have this first equation. So we know we want to reach a velocity of 2 meters, of 2 meters per second at the end. So we'll end up getting 4 is equal to 2a times 10. So our a is going to be 0.20 meters per second squared because our delta x is 10 meters. So multiply that 0.20 meters per second squared times our mass, and that gives us ma. So essentially we get tr is equal to m into g minus a, which will give us 768 newtons. So this is going to be our tension of the rope, which we're going to need in the future. So now going on to this problem, we want to know the angular acceleration. So we already have the acceleration, translational, and we want angular acceleration, and we have the radius. So we just set up our equation. So we have 0.20 meters per second squared is going to be equal to 0.80 meters into alpha. So our alpha is going to then be equal to 0.25 radians per second squared. Now, what we really want to do is, if we want to find our moment of inertia, we need to also calculate torque, which is where the tension of the rope comes in up there. And what we're going to do is, we know that net torque is equal to moment of inertia into alpha. So moment of inertia is equal to torque divided by alpha. And looking at our force diagrams up there, we know that the only force acting on this flywheel right now that exerts a torque is going to be the tension of the rope. So torque is just essentially going to be tension of the rope into R. So from there, we know, just plugging this in, that the tension of the rope force was 768 newtons times its R away from the center. So times 0.80 meters divided by our alpha, which is 0.25 radians per second squared. Which, plugging these numbers, you will get our moment of inertia equal to 2,457.6 kilograms meters squared. Now that we know the moment of inertia and we've solved basically our first part of this, we want to also figure out what our mass is. So because this is just a huge, solid, uniform cylinder, it's going to have a moment of inertia equal to half mr squared. So plug in our I value for I in here, so half mr squared is equal to 2,457.6 kilogram meters squared. Plug in our radius, which is 0.80 meters, and you just solve this equation for m, and you get 7,680 kilograms. Cool.